Let me tell you about something so extraordinary, so mind-bending, that even after decades of studying physics, it still fills me with awe. Black holes, those cosmic monsters that devour everything that crosses their path, from which not even light can escape, might not be dead ends at all. They might be the opposite. They might be cosmic wombs, doorways, Genesis engines, black holes, birth universes. This isn't science fiction. This isn't speculation pulled from thin air. This is a serious scientific hypothesis, supported by theoretical physics, taken seriously by cosmologists, and with implications so profound that they force us to completely reimagine what reality is. Every black hole in our universe, and there are billions of them, perhaps hundreds of billions, might contain within it an entirely new universe, a cosmos as vast as our own, with its own galaxies, its own stars, its own planets, perhaps its own life. And our universe, our entire observable cosmos, with its 2 trillion galaxies and its 100 billion trillion stars, it might exist inside a black hole in some larger parent universe. This is the theory of cosmological natural selection. It's the hypothesis that black holes are not endpoints but beginnings. And understanding it requires us to journey into the strangest territory physics has ever explored. Let me start at the beginning with what we actually know about black holes. A black hole forms when a massive star dies. Throughout its life, a star is engaged in a constant battle. Gravity tries to crush it inward, while the energy from nuclear fusion in its core pushes outward. These forces balance, and the star remains stable. But eventually, the star runs out of fuel, fusion slows, then stops, and without the outward pressure to resist it, gravity wins. For stars below a certain mass, the collapse stops at some intermediate stage. The star becomes a white dwarf or a neutron star, incredibly dense but still stable. But for stars above, about 25 times the mass of our sun, nothing can stop the collapse. The star falls in on itself, crushing matter to infinite density, warping space-time beyond recognition. What remains is a black hole, a region of space where gravity is so strong that nothing can escape. The boundary of this region is called the event horizon, not a physical surface, but a point of no return. Cross the event horizon, and you're falling toward the center, inevitably, inescapably. At the center of the black hole, according to general relativity, lies a singularity, a point of infinite density, where space-time curvature becomes infinite, where the known laws of physics break down completely. The singularity is where things get interesting. And by interesting, I mean completely insane. You see, general relativity, Einstein's theory of gravity, is an extraordinarily successful theory. It's been tested countless times and has passed every test. It predicts the bending of light around massive objects, the gravitational redshift, the existence of gravitational waves, all confirmed. But general relativity has a problem. It predicts its own breakdown. At the singularity inside a black hole, the theory gives infinite answers, infinite density, infinite curvature. Mathematically, the equations explode. When a physical theory gives infinite answers, it's telling us something important. The theory is incomplete. Something is missing. At the singularity, general relativity is screaming for help, screaming for a more complete theory that can handle these extreme conditions. That more complete theory would be quantum gravity, a theory that unifies Einstein's general relativity with quantum mechanics. We don't have a complete theory of quantum gravity yet. It's one of the holy grails of physics. But we have glimpses, hints, partial theories that point the way. And those theories suggest something remarkable about singularities. They might not be points of infinite density after all. They might be something else entirely. Let me explain what quantum mechanics does to singularities. In quantum mechanics, there's a fundamental principle called the uncertainty principle. It says you cannot know both the position and the momentum of a particle with perfect precision. The more precisely you know one, the less precisely you can know the other. This principle has profound implications for singularities. A classical singularity, the kind predicted by general relativity, is a point with zero size and infinite density. But quantum mechanics doesn't allow such precision. If you try to confine matter to a point of zero size, the uncertainty in its momentum becomes infinite. The matter fights back, resisting confinement. This suggests that quantum gravity might smear out singularities, replacing them with something finite, something with a very small but non-zero size, a very high but finite density. The infinities of general relativity would be tamed by quantum effects. But here's where it gets really interesting. Several approaches to quantum gravity suggest that the singularity doesn't just get smeared out, it does something much more dramatic. It bounces. This is the idea of a quantum bounce, or big bounce. When matter collapses toward a singularity, quantum effects eventually become strong enough to stop the collapse and reverse it. Instead of crushing to infinite density, the matter bounces back, expanding outward again. But expanding into what? Not back into the original universe. The event horizon prevents that. Instead, the bounce might create a new region of space-time, expanding in a direction that's perpendicular to our own, invisible and inaccessible to us. In other words, the bounce might create a new universe. This is not idle speculation. It emerges from serious theoretical work in loop quantum gravity, one of the leading approaches to quantum gravity. Physicists like Lee Smolin, Abhay Ashtekar, and others have developed mathematical models showing how a collapsing black hole could bounce and become an expanding universe. The key insight is that the singularity, far from being an endpoint, could be a transition, a doorway. The death of a star in our universe could be the birth of an entirely new cosmos. Let me try to visualize this, because I know it's mind-bending. Imagine our universe as a vast sheet stretching in all directions. A black hole forms when a massive star collapses, creating a funnel that stretches down from the sheet, getting narrower and narrower. In classical general relativity, the funnel ends in a point, the singularity. But in quantum gravity, the funnel doesn't end in a point. Instead, it opens up again on the other side, blossoming into a new sheet, a new universe. From our perspective, looking at the black hole from outside, we see nothing unusual, just a black sphere in space absorbing anything that falls into it. But on the inside, beyond the event horizon, the collapsing matter bounces and begins to expand. A new universe is born, growing and evolving, eventually containing galaxies and stars of its own. This new universe is connected to ours by a kind of umbilical cord, a throat or bridge through space-time. But we can never access it. The event horizon blocks any passage. The new universe is causally disconnected from ours, as unreachable as if it were infinitely far away. And here's what's even more mind-blowing. If this picture is correct, then our universe might have been born the same way. Our Big Bang might have been a quantum bounce inside a black hole in some parent universe. Think about that for a moment. The Big Bang, the beginning of everything we know, the origin of space and time and matter, might have been what it looks like from the inside when a star collapses in another universe. Our entire cosmos, everything we can see, everything we can measure, all 2 trillion galaxies and the 100 billion trillion stars they contain, all of it might exist inside a black hole. We are inside a black hole. And we don't notice because from the inside, it doesn't look like a black hole. It looks like an expanding universe. It looks like home. Now let me tell you about the physicist who developed this into a full cosmological theory, Lee Smolin. Smolin is a theoretical physicist at the Perimeter Institute in Canada, one of the leading researchers in quantum gravity. In the 1990s, he proposed a remarkable theory called cosmological natural selection. The idea is simple but profound. If black holes create new universes, and if the physical constants in the new universe are slightly different from the parent universe, varying randomly with each generation, then universes will evolve over time, just like biological organisms. Why? Because some universes will produce more black holes than others. The constants of physics, the strength of gravity, the masses of particles, the charges of quarks affect how stars form, how they evolve, and how many of them become massive enough to collapse into black holes. A universe whose constants allow for many black holes will have many offspring. A universe whose constants prevent black hole formation will have few or no offspring. Over many generations, the population of universes will be dominated by those whose constants are optimized for black hole production. This is natural selection applied to cosmology. Universes that are good at making black holes reproduce more and their properties spread through the multiverse. Universes that are bad at making black holes go extinct. And here's the remarkable thing. A universe optimized for black hole production looks a lot like our universe. To make black holes, you need massive stars. To get massive stars, you need nuclear fusion to work in a particular way. You need gravity to be strong enough to compress gas clouds into stars, but not so strong that everything collapses immediately. You need the nuclear force to be tuned so that hydrogen can fuse into helium and heavier elements, releasing energy and allowing stars to shine for millions of years before dying. All of these requirements, the conditions for making lots of black holes, turn out to be almost exactly the conditions needed for life. A universe with stars that burn long enough to form black holes is a universe with stars that burn long enough for planets to form around them. A universe with the right chemistry for stellar nucleosynthesis is a universe with the right chemistry for complex molecules, including the molecules of life. This might solve one of the great mysteries of physics, the fine-tuning problem. The constants of physics seem suspiciously well suited for life. If gravity were slightly stronger, stars would burn too fast. If it were slightly weaker, they might not ignite at all. If the nuclear force were different, fusion wouldn't work, and there would be no heavy elements. If the cosmological constant were larger, the universe would have expanded too fast for galaxies to form. Why are the constants just right? Traditional physics has no answer. It's either a remarkable coincidence or there's some deep principle we don't understand. Cosmological natural selection offers an answer. The constants are fine-tuned for black holes, and the conditions for black holes happen to overlap with the conditions for life. We exist because we're in a universe that's good at making black holes, and good at making black holes means good at making the conditions for complexity, chemistry, and life. It's a beautiful theory, elegant, explanatory, and testable, which is more than can be said for many multiverse theories. Smolin made specific predictions that could, in principle, be checked. For example, he predicted that no change to the constants of physics could increase the number of black holes our universe produces. If you could tweak any constant and show that it would make more black holes, the theory would be falsified. This prediction has been explored but not definitively confirmed or refuted. The calculations are difficult, and we don't fully understand all the factors that affect black hole formation. But the theory remains viable, and the prediction remains a target for future research. In part 2, I want to go deeper into the physics of how black holes might create universes. I want to explore the mechanism, the mathematics, the mind-bending geometry of what happens inside an event horizon. Because understanding how this works requires us to push the boundaries of everything we know about space, time, and the nature of reality itself. So we've established the extraordinary hypothesis: black holes might not be cosmic dead ends, but cosmic wombs birthing entire universes within their event horizons. We've encountered Lee Smolin's theory of cosmological natural selection, which suggests that universes evolve over generations, with those producing more black holes dominating the cosmic population. Now I want to take you deeper. I want to explore the physics of how this might actually work, the mechanisms, the mathematics, the geometry of space-time that would allow a collapsing star in our universe to become an expanding cosmos somewhere else. Because this isn't just wild speculation. It emerges from our best attempts to understand the deepest laws of nature. Let me start with what happens when you fall into a black hole. From the outside, a black hole looks simple. There's an event horizon, a spherical boundary marking the point of no return. Cross it, and you can never escape. The event horizon isn't a physical surface. It's a mathematical boundary defined by the curvature of space-time. But what does it look like from the inside? What would you experience if you fell into a black hole? For a large black hole, 1 millions or billions of times the mass of the sun, like the supermassive black holes at the centers of galaxies, you might not notice anything special as you cross the event horizon. The tidal forces would be gentle, at least initially. You'd cross from the outside to the inside without drama. But once inside, something profound has changed. Space and time have switched roles. This is one of the strangest features of black hole physics. Outside the event horizon, you can move freely in space, left or right, up or down, forward or backward, but you're constrained in time. You can only move forward into the future. Inside the event horizon, this reverses. Now, you can move freely in time in a certain mathematical sense, but you're constrained in space. Specifically, you must move toward the singularity. It's not that something is pulling you toward the singularity. It's that all directions in space point toward the singularity. The singularity is not a place in space, it's a moment in time. Your future, no matter which direction you try to move, you're moving toward the singularity, just as no matter which direction you move outside the black hole, you're moving toward the future. The singularity is inevitable, inescapable, the final destination of all world lines inside the event horizon. At least that's what classical general relativity says. But we've already discussed how classical general relativity breaks down at the singularity. The theory gives infinite answers, which means it's telling us it's incomplete. Quantum effects must become important. And when we incorporate quantum effects, the story changes dramatically. Let me tell you about loop quantum gravity, because this is where some of the most detailed work on black hole interiors has been done. Loop quantum gravity is one of the leading approaches to quantum gravity. It proposes that space itself is quantized, made up of discrete units at the smallest scales, rather than being continuous. These units are incredibly small, on the order of the Planck length, about 10 negative 35 meters, far smaller than any particle we've ever detected. In loop quantum gravity, the smooth fabric of space-time that Einstein described is an approximation. At the Planck scale, space-time has a discrete, granular structure, like a fabric woven from tiny threads. This discreteness has profound implications for singularities. In classical general relativity, a singularity is a point of infinite density matter crushed to zero volume. But in loop quantum gravity, you can't have zero volume. Space has a minimum quantum of size. You can't squeeze anything smaller than the Planck length. So when matter collapses toward a singularity, the quantum structure of space pushes back, the collapse slows, then stops, then reverses. The singularity is replaced by a quantum bounce. Physicists Abhay Ashtekar, Tomasz Pawlowski, and Parampreet Singh have worked out detailed mathematical models of this process. They've shown that in loop quantum cosmology, the application of loop quantum gravity to the universe as a whole, the Big Bang singularity is replaced by a quantum bounce. Before our universe existed in its current expanding phase, it might have been contracting, getting denser and denser, until quantum gravity effects cause it to bounce and begin expanding. The same logic applies to black holes. The singularity at the center of a black hole might not be a true singularity, but a quantum bounce region, a place where the extreme density triggers a reversal, where collapse becomes expansion. But expansion into what? This is where the geometry gets truly mind-bending. Let me try to explain the geometry of a black hole interior, because it's essential to understanding how a new universe might be born. In classical general relativity, the geometry inside a black hole is described by solutions to Einstein's equations. The most famous is the Schwarzschild solution, which describes a non-rotating, uncharged black hole, but more realistic black holes rotate, and their geometry is described by the Kerr solution. The Kerr solution has a remarkable feature. Inside the event horizon, there's a region called the inner horizon, and beyond that, potentially, a passage to another region of space-time. In the idealized mathematics, this other region is a white hole, the time reverse of a black hole, spewing matter out rather than sucking it in. And the white hole might open into another universe, or another part of our universe, connected by a wormhole or Einstein-Rosen bridge. Now, most physicists believe that this idealized picture doesn't hold up in reality. The inner horizon is unstable. Any perturbation causes it to become a singularity. The wormhole, if it exists at all, would collapse before anything could pass through. But quantum gravity might change this picture. Some researchers have suggested that quantum effects could stabilize the interior structure, preventing the formation of a singularity and allowing for a genuine transition to another region of space-time. This is where the idea of universe creation comes in. The bounce at the would-be singularity doesn't just reverse the collapse within our universe. It creates a new region of space-time, an expanding universe that grows perpendicular to our own in a direction we can't access or perceive. Let me try an analogy. Imagine our universe as a sheet of rubber. A black hole is like a heavy ball placed on the sheet, creating a deep indentation that stretches down. In classical general relativity, the indentation goes down forever, ending in a point. But with quantum gravity, the indentation doesn't end in a point. Instead, it opens up into another sheet, another universe. The rubber stretches down, then blossoms outward, creating a new surface connected to ours by a narrow throat. From our perspective, looking at the black hole from outside, we see nothing unusual. The event horizon looks like a dark sphere. But inside, beyond the horizon, a new universe is inflating, expanding, evolving, completely inaccessible to us. The throat connecting the two universes is incredibly narrow, on the order of the Planck length. No information, no matter, no signal of any kind can pass through. The two universes are causally disconnected, as separate as if they were infinitely far apart. But they're connected by ancestry. Our universe gave birth to the baby universe through the process of gravitational collapse. The matter that fell into the black hole became the seed of a new cosmos. Now let me tell you about something even more extraordinary, the possibility that the laws of physics themselves might be inherited with variations from parent to offspring. In cosmological natural selection, Smolin proposed that when a new universe is born, its fundamental constants, the masses of particles, the strengths of forces, the values of coupling constants are slightly different from the parent universe. The constants mutate randomly with each generation. Why would this happen? We don't have a complete theory, but there are plausible mechanisms. One possibility involves the landscape of string theory. String theory, another approach to quantum gravity, suggests that there are many possible ways for the extra dimensions of space to be curled up and each configuration gives rise to different effective physics in the 4 dimensions we observe. The number of possible configurations is enormous, perhaps 10, 500 or more. This is the string landscape. When a new universe is born, it might randomly select a configuration from this landscape. The selection would be influenced by the parent universe's configuration, but with some random variation. Different configurations mean different effective constants, different particle masses, different force strengths. Another possibility is that the constants are determined by quantum fluctuations at the bounce. In the extreme conditions of the quantum gravity regime, fluctuations in the fields that determine the constants could shift their values randomly. Each bounce would produce slightly different values. Either way, the result is variation. Parent and offspring universes are similar but not identical. The constants drift over generations, exploring the space of possibilities. And this is where natural selection comes in. Some combinations of constants produce universes that make lots of black holes. Stars form, burn, and collapse. Each collapse creates a new universe. These universes are prolific. They have many offspring. Other combinations produce universes that make few or no black holes. Maybe stars don't form because gravity is too weak. Maybe they form but don't collapse because the nuclear force is too strong, preventing stellar death. These universes are sterile. They have few or no offspring. Over many generations, the universes that make lots of black holes come to dominate the population. Their constants spread through the multiverse. The constants that are bad for black hole production disappear because universes with those constants don't reproduce. This is evolution by natural selection, operating at the level of universes. Fitness is measured in black holes. The more black holes you make, the more offspring you have, the more your constants spread. And here's the remarkable prediction. If this theory is correct, our universe's constants should be optimized for black hole production. Any change to the constants making gravity stronger or weaker, changing the mass of the electron, adjusting the nuclear force, should reduce the number of black holes our universe produces, not increase it. This is a testable prediction. In principle, we could calculate how the number of black holes depends on the fundamental constants and check whether our universe sits at a maximum. The calculations are difficult, and the answer isn't entirely clear. Some analyses suggest that our constants are indeed near optimal for black hole production. Others find room for improvement, ways to tweak the constants that might produce more black holes. The jury is still out. But the fact that the theory makes a testable prediction is remarkable. Most multiverse theories are criticized for being untestable. Cosmological natural selection sticks its neck out, making a claim that could, in principle, be falsified. Now let me tell you about some recent developments that have added new dimensions to this picture. One development involves the information paradox. The information paradox is one of the deepest puzzles in black hole physics. When something falls into a black hole, what happens to the information it contained? Classical general relativity says it's lost forever, destroyed at the singularity. But quantum mechanics says information can never be truly destroyed. It's always preserved, even if scrambled beyond recognition. For decades, physicists have debated how to resolve this contradiction. Stephen Hawking, who discovered that black holes radiate and eventually evaporate, initially believed that information was lost. Later, he changed his mind, suggesting that information might be encoded in subtle correlations in the Hawking radiation. Recent work has shed new light on this puzzle. Research by Ahmed Almheri, Netta Engelhardt, Donald Maroff, Henry Maxfield, and others building on earlier work by Don Page, Patrick Hayden, and John Preskill suggests that information does escape from black holes, but in a subtle and surprising way. What does this have to do with universe creation? The answer involves something called the island formula. The island formula is a new tool for calculating the entropy of Hawking radiation, the disorder in the particles emitted by a black hole. It suggests that the interior of a black hole can be reconstructed in principle from the radiation it emits. But here's the twist. The island, the interior region of the black hole, might not be inside our universe at all. It might be in a different region of space-time, disconnected from ours. In other words, the interior of the black hole might be a baby universe. This connects the information paradox to universe creation. The information that falls into a black hole might not be destroyed, and it might not escape into our universe either. It might end up in the baby universe, seeding its initial conditions. The matter and information that collapse into a black hole become the raw material for a new cosmos. Nothing is lost, it's just transferred to the offspring universe, where it begins a new life. This is speculative, but it's being taken seriously by researchers at the frontier of theoretical physics. The information paradox in universe creation might be two aspects of the same phenomenon. Another recent development involves primordial black holes. Primordial black holes are hypothetical black holes that might have formed in the early universe, not from stellar collapse, but from density fluctuations in the hot plasma of the Big Bang. If regions of the early universe were dense enough, they could have collapsed directly into black holes without ever becoming stars. Recent observations have renewed interest in primordial black holes. The gravitational wave detectors, LIGO and Virgo, have detected mergers of black holes that are surprisingly heavy, heavier than stellar models easily explain. Some researchers have suggested that these might be primordial black holes. If primordial black holes exist, they add to the population of black holes in our universe and thus to the number of offspring universes. A universe that produces both stellar black holes and primordial black holes would be even more prolific than one that produces only stellar black holes. This could affect cosmological natural selection. If the conditions for primordial black hole formation are different from the conditions for stellar black holes, then the constants of physics might be optimized for both. The theory becomes richer, with more predictions and more opportunities for testing. There's also recent work on the connection between black holes and the cosmological constant. The cosmological constant is the energy density of empty space, the famous dark energy that's causing the universe's expansion to accelerate. It's extremely small, about 10 negative 123 inches natural units. This tiny value is one of the biggest puzzles in physics. Why is it so small but not zero? Some researchers have suggested a connection between the cosmological constant and black holes. In certain theories, the cosmological constant might decrease every time a black hole forms, as if black holes eat vacuum energy. If this is correct, then universes with lots of black holes would naturally evolve towards small cosmological constants. Cosmological natural selection would favor not just black hole production, but also the conditions that lead to a small cosmological constant, which happens to be the condition that allows for long-lived universes with complex structures. This would connect two of the great fine-tuning puzzles. Why are the constants right for black holes, and why is the cosmological constant so small? Cosmological natural selection might answer both. Let me now step back and consider what all this means for our understanding of the universe. If black holes create new universes, then the cosmos is far vaster and stranger than we ever imagined. Our observable universe, the part we can see, with its 2 trillion galaxies, is just one bubble in an infinite froth of universes, each one born from a black hole in a parent universe, each one giving birth to countless offspring through its own black holes. This is not a static multiverse, but a dynamic one. Universes evolve over generations. The constants of physics change, exploring the landscape of possibilities. Successful universes, those that make lots of black holes, proliferate. Unsuccessful ones die out. There's a kind of cosmic ecology at work. Universes compete for existence by competing to produce offspring. The fittest universes, the ones best at making black holes, come to dominate the population, and we exist because we're in a fit universe. Our constants are fine-tuned not by a designer, but by selection. Countless universes with different constants existed, most of them barren, most of them leaving no descendants. We're one of the lucky ones, one that makes stars that burn for billions of years, that forge heavy elements in their cores, that collapse into black holes when they die. We're here because our universe is good at reproduction, and we might be evidence of its fertility complex beings made of star stuff, contemplating the black holes that made our existence possible. In part 3, I want to explore the deepest implications of this picture. What does it mean for our understanding of existence? For the question of why there's something rather than nothing? For our place in a cosmos that births new realities from the hearts of dying stars? Because if black holes truly birth universes, then the universe is not just stranger than we imagined, it's stranger than we can imagine. So we've journeyed through the extraordinary physics of black holes as universe creators. We've seen how quantum gravity might replace singularities with bounces, how collapsing matter in our universe might become expanding space-time in a baby universe, and how cosmological natural selection might explain why our universe has the constants it has. Now I want to explore the deepest implications of this picture. What does it mean for our understanding of existence? For the question of why there's something rather than nothing? For our place in a cosmos that births new realities from the hearts of dying stars? And what are the philosophical, scientific, and even spiritual implications of living in a universe that is itself a child of another universe and that gives birth to countless universes of its own? Let me start with the question of origins, the deepest question humans have ever asked. Where did the universe come from? Why does anything exist at all? For most of human history, these questions were answered by creation myths, stories of gods or cosmic forces bringing the world into being. In the scientific age, we've replaced these myths with physical theories. But the fundamental question remains, why is there something rather than nothing? The standard cosmological picture of the Big Bang describes how our universe evolved from a hot, dense state about 13.8 billion years ago. But it doesn't explain where that initial state came from. The Big Bang is a description of how the universe evolved, not an explanation of why it exists. Cosmological natural selection offers a different perspective. In this picture, our universe didn't come from nothing. It came from something apparent universe, a black hole, a process of gravitational collapse and quantum bounce. The Big Bang wasn't the absolute beginning. It was a transition, a moment when matter that had collapsed in another universe bounced and began expanding in ours. Our cosmic origin wasn't creation from nothing, but birth from something. This doesn't fully resolve the question of origins, of course. You can still ask, where did the parent universe come from? And its parent? Is there an infinite regress of universes, each one born from a black hole in the previous? Some versions of the theory suggest exactly this, an eternal process of universe creation with no beginning and no end. Universes have always been giving birth to new universes, and always will be. There's no first universe, no ultimate origin, just an eternal cycle of cosmic reproduction. This is a strange picture, but it's not incoherent. We're used to thinking that everything must have a beginning, but this might be a bias of our evolved minds rather than a truth about reality. An infinite past is conceptually challenging, but not logically impossible. Alternatively, there might be a first universe, in some sense, a ground-level reality from which all others descend. But this first universe might not have come from nothing either. It might be eternal, existing timelessly, with no beginning or end, or it might have emerge from some pre-geometric state, a quantum fluctuation in a realm where time and space don't yet exist? The honest answer is that we don't know. Cosmological natural selection pushes the question of ultimate origins back, but it doesn't fully answer it. What it does is show that the question might be different from what we thought. The Big Bang might not be the beginning of everything, just the beginning of our particular branch on an infinite tree of universes. Now let me explore what this picture means for the concept of design. One of the oldest arguments for the existence of God is the argument from design. The universe seems fine-tuned for life. The constants of physics are just right for stars, planets, and chemistry. This fine-tuning seems to cry out for explanation, and traditionally, the explanation has been a designer. God tuned the constants to allow for life. Cosmological natural selection offers an alternative explanation that doesn't require a designer. The constants are fine-tuned not because someone chose them, but because selection favored them. Universes with the right constants for black holes proliferate, others don't. We find ourselves in a universe with life-friendly constants because those constants are also black hole friendly, and black hole friendly universes are the ones that dominate the cosmic population. This is similar to how biological evolution explains the apparent design of organisms. Eyes seem designed for seeing, wings for flying, hearts for pumping blood. But Darwin showed that this apparent design emerges from natural selection without any designer. Organisms that see better, fly better, pump blood better, leave more offspring. Over generations, adaptations accumulate, producing the appearance of design. Cosmological natural selection applies the same logic to universes. Universes that make more black holes have more offspring. Over generations, the constants that favor black hole production spread through the multiverse. The result is universes that look designed for black holes and, incidentally, for life. This doesn't disprove the existence of God, of course. A theist could argue that God designed the process of cosmological natural selection itself, or that God exists alongside natural explanations. But it does show that design arguments aren't compelling. We don't need a designer to explain fine-tuning if selection can do the job. There's something beautiful about this picture. The universe isn't fine-tuned by a distant supernatural designer. It's fine-tuned by a process, a natural physical process of cosmic evolution. The universe is self-tuning, self-organizing, self-creating. It generates its own order through the blind mechanism of selection. This is the same beauty we find in biological evolution. Life isn't designed, it evolves. The intricate complexity of organisms emerges from simple rules operating over billions of years. No designer is needed because selection is enough. Cosmological natural selection extends this insight to the cosmos itself. The universe isn't designed, it evolves. The fine-tuning of physics emerges from simple rules, the rules of quantum gravity and cosmic reproduction operating over countless generations of universes. No cosmic designer is needed because cosmic selection is enough. Now let me consider what this picture means for the question of meaning. If the universe is a product of blind selection, does that make it meaningless? If we exist not because we were intended, but because we happen to be in a universe that's good at making black holes, does that diminish our significance? I don't think so. In fact, I think the opposite is true. Consider biological evolution. When Darwin first proposed that humans evolved from apes, many people felt diminished. We weren't specially created, we were just another animal, a product of the same blind process that produced worms and bacteria. But over time, many people have come to see evolution as enhancing human significance rather than diminishing it. We're connected to all life on Earth, part of a vast family tree that stretches back billions of years. We're made of star stuff, children of ancient generations, carriers of a legacy that began in the primordial oceans. The same reframing applies to cosmological natural selection. We're not specially created, we're products of a blind cosmic process. But this process connects us to something vast, an infinite tree of universes, a cosmic ecology of reproduction and selection. We're not isolated in a single arbitrary cosmos. We're part of a cosmic lineage, descended from countless parent universes, ancestral to countless offspring. Our universe is a link in an infinite chain, a node in an eternal network of cosmic reproduction. And we're not accidents. We exist because our universe is fit because it has the right constants for black holes and incidentally for life. Our existence isn't arbitrary. It's the result of selection. We're here because universes like ours proliferate, and universes like ours are the kind that produce complexity and consciousness. This doesn't give us cosmic importance in the sense of being designed or intended, but it does give us a place in the cosmic order, a place earned by the fitness of our universe, a place in a process that spans infinitely many realities. There's meaning in that. Not imposed meaning from a designer, but emergent meaning from a process. We're meaningful because we're connected to the vast web of cosmic evolution, connected to the black holes that birthed our universe, connected to the baby universes that our black holes are birthing right now. Let me now explore what this picture means for the future. If black holes create new universes, then the cosmos has a future as well as a past. New universes are being born right now from the black holes in our universe. And our universe will continue to produce black holes for billions of years to come, each one potentially birthing a new cosmos. What will these offspring universes be like? If cosmological natural selection is correct, they'll be similar to ours, but not identical. The constants will have mutated slightly, exploring nearby regions of the parameter space. Most will still be fit, still capable of making stars and black holes, still hospitable to complexity, but some might have drifted into infertile regions, becoming sterile, leaving no descendants of their own. The cosmic tree will continue to grow, branching and branching, exploring the landscape of possible physics. Some branches will flourish, others will wither. The process will continue indefinitely as long as there are universes capable of making black holes. And what about the far future of our universe? Current cosmology predicts that our universe will expand forever, driven by dark energy. Over trillions of years, galaxies will drift apart, stars will burn out, and the cosmos will fade into a cold, dark, empty state. This is the heat death, the ultimate fate of a universe dominated by entropy. But even in the heat death, black holes will remain at least for a while. Black holes evaporate through Hawking radiation, but slowly. A stellar mass black hole would take about 1067 years to evaporate. A supermassive black hole might last 100 years or more. During all this time, the black holes would continue to create baby universes. Even as our universe fades into darkness, it would be giving birth to new cosmoses, each one starting fresh, each one beginning its own journey of expansion and evolution. In a sense, our universe's death would be another universe's birth. The end isn't really an end, it's a transition. The matter and energy of our cosmos would be recycled into new realities, continuing the cosmic process indefinitely. This is a strangely comforting picture. The universe isn't heading toward final oblivion, it's heading toward transformation, a transformation in which its substance is passed on to new generations, like parents passing their legacy to children. We won't be there to see it, of course. Humanity, or whatever we evolve into, will be long gone before the last black holes evaporate. But our contribution will remain. The black holes, created by the deaths of stars, that were born from clouds that contained atoms forged in ancient supernovae, atoms that were once part of planets, of living things, of us, those black holes, might carry some trace of our existence into new universes. It's a tenuous connection, but a connection nonetheless. We're part of a process that will continue forever, or at least for as long as forever has meaning. Now let me address some objections and alternatives to this picture. The most serious objection to cosmological natural selection is that we don't fully understand quantum gravity. The theory depends on the existence of quantum bounces inside black holes, on the creation of baby universes, on the mutation of physical constants. All of these are speculative, beyond the reach of current experiments. This is a fair criticism. We don't have a complete theory of quantum gravity. Loop quantum gravity, which provides some of the technical foundations for cosmological natural selection, is still under development. String theory, the main competitor, suggests a different picture, one where the landscape of possible physics is fixed and different regions of the multiverse correspond to different vacua rather than different generations. But speculation is not the same as fantasy. Cosmological natural selection is a serious scientific hypothesis based on our best understanding of physics, making predictions that can in principle be tested. It might be wrong, but it's not unscientific. And the basic idea that black holes might create new regions of space-time is not unique to loop quantum gravity. Similar ideas arise in other approaches to quantum gravity, in studies of the black hole information paradox, and in theoretical work on the nature of singularities. The details vary, but the theme recurs. Singularities might not be endpoints, but transitions. Another objection is that cosmological natural selection might not be the only explanation for fine-tuning. The multiverse of eternal inflation, where different regions have different constants due to random quantum fluctuations, could also explain why we observe life-friendly physics. If infinitely many regions exist with all possible constants, we'd obviously find ourselves in a region compatible with our existence. This is the anthropic explanation, and it's a serious alternative. But it has a weakness. It doesn't make specific predictions. Any constants compatible with observers are equally explained. Cosmological natural selection makes a stronger prediction. The constants should be optimized for black holes, not just compatible with life. This difference, in principle, allows the two theories to be distinguished. If we could calculate the constants that maximize black hole production, we could check whether our universe's constants match. The calculations are difficult, but the test is well defined. There's also the objection that we have no direct evidence for baby universes. We can't see them, communicate with them, or detect them in any way. How can we claim they exist? This objection applies to all multiverse theories, not just cosmological natural selection. And it misunderstands how science works. We don't always have direct evidence for the entities our theories posit. We have no direct evidence for quarks. We infer them from the patterns in particle physics. We have no direct evidence for the cores of stars. We infer them from stellar models and nuclear physics. The same logic applies to baby universes. We infer them from our theories of quantum gravity and black hole physics. The theories make predictions about things we can observe, the patterns in the cosmic microwave background, the distribution of black holes, the values of physical constants. If the predictions match, we have evidence for the theories, including the parts we can't directly observe. Science often works by inference to the best explanation. We accept the existence of entities we can't see because they're part of theories that explain what we can see. Baby universes might be in this category, unseen but inferred, theoretical but real. Let me now explore some deeper philosophical implications. Consider the question of identity. If every black hole creates a new universe, and our universe contains billions of black holes, then we're constantly giving birth to new cosmoses. In what sense are those cosmoses related to us? There's a kind of cosmic parenthood at work. Our universe is the parent. The baby universes are offspring. The offspring inherit their properties from the parent, modified by mutation, but still recognizably related. Over generations, a lineage develops, a family tree of universes connected by descent. This invites us to think about cosmic identity in genealogical terms. Just as you're related to your parents, grandparents, and ancestors, stretching back into prehistory, our universe is related to its parent universe, grandparent universe, and ancestors stretching back through cosmic history. And just as you're related to your children, grandchildren, and descendants stretching into the future, our universe is related to the baby universes being born in its black holes and to their descendants stretching forward through cosmic time. We're part of a family, a cosmic family, spanning infinitely many generations, connected by the process of gravitational collapse and quantum bounce. This changes how we should think about ourselves. We're not isolated beings in an isolated cosmos. We're part of a lineage, a tradition, a flow of cosmic inheritance that stretches beyond anything we can observe or comprehend. Consider also the question of teleology, purpose, direction, goal. In ordinary natural selection, there's no teleology. Evolution doesn't have a purpose. It just happens. Organisms don't evolve toward anything. They just adapt to their current environments. The appearance of progress is an illusion. There's no direction built into the process. The same is true of cosmological natural selection. Universes don't evolve toward anything. They just reproduce, with the most reproductive ones coming to dominate. There's no cosmic goal, no ultimate purpose, no direction the multiverse is heading. And yet there's something that looks like direction, something that emerges from the process even though it's not built in. Over time, cosmological natural selection produces universes that are increasingly good at making black holes. The constants converge toward optimal values. The parameter space is explored, and the fit regions are populated while the unfit regions are abandoned. This looks like progress, even though no one is directing it. The multiverse is getting better at reproduction, even though no one is trying to improve it. Similarly, fit universes are more likely to produce complexity stars, planets, chemistry, life. Cosmological natural selection might favor not just black holes, but the conditions for intelligence. Universes with observers might be more fit than universes without if observers somehow contribute to black hole production. This is speculative, but not crazy. There have been proposals that advanced civilizations might create black holes artificially through technological means, through the manipulation of matter and energy on cosmic scales. If this is possible, then universes that produce intelligent life might produce more black holes than universes that don't. In this case, cosmological natural selection would favor intelligence. The multiverse would evolve toward ever more intelligent inhabitants, not because intelligence is the goal, but because intelligence contributes to fitness. This is a remarkable possibility. It suggests that we conscious beings, intelligent observers, might not be cosmic accidents. We might be part of the fitness landscape, contributors to our universe's reproductive success. I don't want to overstate this. We have no evidence that civilizations create black holes. And even if they do, it's not clear that the contribution would be significant compared to natural black hole formation. But the possibility is intriguing, a hint that consciousness might have cosmic significance after all. Now let me consider what cosmological natural selection means for the nature of physical law. We usually think of the laws of physics as fixed and eternal. The constants have the values they have, and that's that. We might discover what those values are, but we don't expect them to change or to have a history. Cosmological natural selection challenges this view. In this picture, the constants do have a history. They evolved generation by generation through the process of cosmic reproduction. The values we observe today are the result of billions of generations of selection, exploring the landscape of possibilities and converging on fit values. This means the laws of physics are, in a sense, contingent. They didn't have to be what they are. They're not necessary truths, but evolved outcomes. Different histories would have led to different laws. This is a profound shift in perspective. The laws of physics are not eternal verities inscribed in the fabric of reality. They're adaptations, fine-tuned by selection, as contingent and historical as the shape of a bird's wing or the structure of an eye. Some people might find this diminishing. The laws of physics seem majestic, eternal, necessary. Now they seem accidental, evolved, arbitrary. But I think the opposite perspective is also valid. The laws are not arbitrary. They're optimized. They're not accidental. They're selected. They represent the outcome of a vast cosmic process, a process that explored countless possibilities and converged on what we observe. There's a different kind of majesty in this, not the majesty of eternal necessity, but the majesty of evolved perfection. The laws are fine-tuned not by a designer, but by a process. They carry the history of countless generations, the legacy of cosmic selection stretching back through infinite time. Let me now consider what cosmological natural selection means for the relationship between physics and biology. One of the most striking features of the theory is that it applies biological concepts, reproduction, selection, fitness, evolution, to the physical universe. This is not just a metaphor. The theory proposes that universes literally reproduce, that they literally undergo selection, that they literally evolve. This suggests a deep unity between physics and biology. The same principles that govern the evolution of life might govern the evolution of universes. Selection, which seemed like a peculiarly biological process, might be a universal principle operating at every scale from organisms to cosmoses. This is a remarkable convergence. For centuries, physics and biology seemed like separate domains, governed by different principles. Physics was about laws and equations, deterministic and mathematical. Biology was about organisms and evolution, historical and contingent. Cosmological natural selection bridges this divide. It shows that evolution can happen at the physical level, that selection can operate on the laws themselves. The universe is not just a stage on which biological evolution plays out. It's a participant in evolution, an evolving entity in its own right. This has implications for how we understand life. If the universe is evolving, if it's becoming increasingly fit for black holes and complexity, then life might not be an accident. Life might be part of the cosmic process, a contributor to the universe's fitness, a product of the same selection that shaped the physical constants. We're not just in the universe, we're of the universe. We're not just observers of cosmic evolution, we're participants in it. Our existence is connected to the universe's fitness, our fate bound up with the cosmic process of reproduction and selection. Now let me explore some even more speculative possibilities. What if universes can not only reproduce but also communicate? What if information can flow between parent and offspring, not through the throat of the black hole, but through the structure of physical law? This is highly speculative, but consider the constants of physics in the offspring universe are inherited from the parent with mutation. This inheritance is itself a kind of information transfer. The offspring knows something about its parent, encoded in its physical constants. Could more information be transferred? Could the structure of the baby universe encode details about the parent's history, its development, its contents? Could there be a kind of cosmic genetics where complex information is passed from generation to generation? We have no evidence for this, but it's not impossible. The process of cosmological natural selection, if it occurs, must involve some mechanism for the inheritance of physical parameters. That mechanism might be simple, just random mutation around the parent's values, or it might be more complex, encoding more information in ways we don't yet understand. If complex information could be inherited, then cosmic evolution might become more than just optimization for black holes. It might become something richer, a cumulative process where each generation builds on the last, where complexity accumulates over cosmic time. This would be analogous to cultural evolution in biology, where information is transmitted not just genetically, but through learning and communication. Cosmic cultural evolution would transmit information between universes, allowing for cumulative improvement beyond what simple genetic mutation could achieve. I'm not claiming this happens. I'm just noting that it's a possibility, a way that cosmological natural selection might be even richer than currently conceived. Another speculative possibility involves the role of consciousness. I mentioned earlier that advanced civilizations might create black holes artificially, contributing to their universe's fitness. But what if consciousness has an even deeper role? Some physicists have speculated that consciousness might be connected to quantum mechanics, that the act of observation, of consciousness apprehending the world, might play a role in the quantum measurement process. This is controversial, and most physicists reject it, but it remains a topic of debate. If consciousness does play a role in quantum mechanics, then it might also play a role in quantum gravity and in the process of universe creation. The formation of a black hole, the quantum bounce, the birth of a baby universe, all of these are quantum gravitational processes. If consciousness affects quantum mechanics, it might affect these processes too. This is wild speculation, but it opens up strange possibilities. What if conscious observation affects the constants of physics in baby universes? What if the mental states of observers at the moment of black hole formation influence the properties of the offspring cosmos? This would give consciousness a cosmic role beyond anything we've imagined. We wouldn't just be observers of the universe, we'd be co-creators of future universes, shaping the multiverse through our observations and thoughts. I emphasize that this is speculative, far beyond what current physics supports. But it illustrates how the picture of black holes birthing universes opens up conceptual space, inviting us to reimagine the relationship between mind and cosmos. Let me now consider what cosmological natural selection means for the question of cosmic significance, whether the universe has value, whether existence matters. In the traditional picture, the universe just is. It exists, governed by fixed laws, heading toward heat death. There's no purpose, no meaning, no direction. The universe doesn't care about anything because it's not the kind of thing that can care. Cosmological natural selection doesn't change this in any direct way. The process of cosmic reproduction is blind, lacking intention or purpose. Universes don't try to make black holes. They just do or don't based on their physics. There's no cosmic mind guiding the process, no purpose behind the selection. And yet the result is a multiverse that has direction, that improves over time, that becomes increasingly good at reproduction. The process generates order, optimization, something that looks like purpose even though it isn't. This is the same paradox we find in biological evolution. Evolution is blind, but it produces adaptation. There's no purpose behind natural selection, but the result is organisms that function as if designed for their environments. Some philosophers have argued that this emergent purpose is genuine, that function and adaptation constitute a kind of meaning even without intentional design. A heart has the purpose of pumping blood, not because someone designed it for that purpose, but because pumping blood is what it was selected for. The same might be true of the multiverse. Universes have the purpose of making black holes, not because someone designed them for that purpose, but because making black holes is what they were selected for. The multiverse has direction, not because someone is steering it, but because selection generates direction from randomness. This is a naturalized, evolved form of cosmic purpose. It's not the grand purpose of traditional theology, the universe fulfilling God's plan, but it's not meaningless either. The universe is going somewhere, even if no one chose the destination. And we're part of it. Our existence is connected to the cosmic process, our lives embedded in a multiverse that evolves and improves over generations. We're not isolated, we're connected. We're not accidents, we're products of selection. We're not meaningless, we're meaningful in the context of a process that generates meaning without intention. This is a strange kind of meaning, naturalized, evolved, emergent, but it's meaning nonetheless. The universe matters because it's part of something larger, and we matter because we're part of the universe. Now, let me bring this to a close with some reflections on what we've learned. Black holes might birth universes. This extraordinary hypothesis emerges from our best attempts to understand quantum gravity, the information paradox, and the fine-tuning of physical constants. It suggests that our universe is not alone, but part of an infinite family, connected by cosmic reproduction to ancestors and descendants beyond our ability to observe. This picture has profound implications. It suggests a new answer to the question of origins. Our universe came from a parent universe through the process of gravitational collapse and quantum bounce. It offers a naturalized explanation for fine-tuning. The constants evolve through selection, not design. It connects physics and biology, showing that selection operates at every scale. And it gives us a new understanding of our place in the cosmos, not as isolated accidents, but as participants in an infinite process of cosmic evolution. The picture is speculative, of course. We don't have a complete theory of quantum gravity. We can't observe baby universes directly. The calculations of cosmological natural selection are difficult and contested. But the picture is also beautiful. It shows the universe as creative, generative, fertile. It shows existence as a process, not a static arrangement. It shows reality as deeper and stranger than we imagined, with layers upon layers of universes nested within each other, connected by black holes, evolving through selection. And it shows us, as part of this process, we're made of atoms forged in stars that will someday die and collapse into black holes. Those black holes will birth new universes, carrying the legacy of our cosmos into new realities. We're not separate from the cosmic process, we're woven into it. Our existence is bound up with the fate of black holes, the evolution of universes, the infinite unfolding of the multiverse. Black holes birth universes, and in some small way, we're part of that birthing products of a universe that was itself born from a black hole, ancestors of universes that will be born from the black holes our matter will someday help create. This is a vision of cosmic interconnection, of deep time and infinite space, of existence as a creative process that spans everything and generates everything. It's a vision that humbles us. We're small, brief, limited, but it's also a vision that elevates us. We're connected to something vast, something infinite, something that matters. The universe is not dead matter and empty space. It's a creative process, generating new realities from the hearts of dying stars. And we're part of it, witnesses to the process, products of the process, participants in the process. Black holes birth universes, and that might be the most beautiful truth physics has ever revealed. We exist because a star died in another universe, collapsed into a black hole, bounced through quantum gravity, and became the Big Bang of our cosmos. And the stars in our universe will die, collapse into black holes, bounce through quantum gravity, and become the Big Bangs of new cosmoses. We are children of black holes, and we are parents of universes yet to be. This is the insane way black holes actually create new universes. And this is what it means to exist in a cosmos that is not an endpoint but a beginning, not a dead end but a doorway, not a final chapter but an eternal story. The story is still being written. New universes are being born right now from the black holes that dot our cosmic landscape. And someday, in the far future, when our sun has burned out and our atoms have scattered, some of that matter might fall into a black hole and help seed a new cosmos. In that new cosmos, billions of years hence, beings might look up at their sky and wonder where their universe came from, and the answer will be from a black hole, from a collapsed star, from a quantum bounce, from us. We are part of the cosmic chain. We are links between past and future, between parent universes and child universes, between what was and what will be. Black holes birth universes, and through them we are connected to infinity.